Okay, good evening. I welcome you all to this core booster series of analog circuits. I am Kiran Kumar, faculty in ACE Engineering Academy. Okay, so with no waste of time, let's dive in. Go through the question once. Find V naught in the steady state if diodes are ideal. The diodes are considered ideal. So, this is a very simple doubler circuit. So, we know during positive cycle D2 is on, the capacitor will charge to 10. During the negative cycle D1 is on and the capacitor will charge to 10 volts with this polarity. So, what is V naught? Try to find V naught by applying KVL in the loop. So, if you apply KVL, it is plus 10 plus V naught plus 10 is 0. So, V naught is going to be minus 20 volts. Now, if the examiner asks you only the magnitude, then it has to be 20. It has to be 20. So, this circuit could be a doubler circuit or a peak to peak detector. Okay. Fine. Go through the question. Find the output voltage V naught if the characteristics of the diode is given. The diode characteristics is given. So, try to model the diodes that are given here. If the diode characteristics would have been a line parallel to y-axis, then the model of the diode would be 0.7 volts. But now you can see that there is a slope here. So, the diode is replaced with 0.7 volts in series with some resistance R, which is 1 by slope. So, slope is 0.1. So, 1 by slope is 10 ohms. So, please replace each diode with 0.7 in series with 10. Okay. So, 1 kilo ohm, each diode is replaced with 0.7 volts in series with 10 ohms. Now, what is given in the problem? You are asked to find V naught. V naught. So, V naught is going to be 10 minus ID into 1K. So, this is V naught. But what is ID in this loop? What is ID in this loop? It is 10 minus 0.7 plus 0.7 plus 0.7. So, your ID is 10 minus 2.1 by 1K plus 3 times of 10. So, this is the solution. So, apply KVL in this loop. So, you get ID and your V naught here is going to be 10 minus drop, 10 minus drop. So, try to find the solution. So, let me calculate 10 minus 2.1 by 1K plus 3 times of 10. I am getting around 2.3. Very good. Aman 2.33 volts. Good, Aman. 2.33 volts. That is the solution. Go through the question. Find the minimum value of RL so that the Zener diode is satisfactorily on if the minimum knee current is 2 milliampere. The current here is 2 milli and Vz is 5 volts. So, how much is Is? Is is 40 minus 5 by 2K. It is around 17.5 milli. So, there is already 2 milli here, simple problem. 17.5 minus 2 is going to be 15.5 milli. The voltage is 5. So, apply Ohm's law and get the value of RL. Apply Ohm's law and get the value of RL. RL is going to be 5 by 15.5 milli. So, get the value of RL 5 by 15.5 milli. How much is this? 5 divided by 15.5 milli. $322 ohms, okay, 322 ohms, good. The RL value is going to be 322, greater than 322 ohms. Go through the circuit, consider the circuit given. The output voltage V0 is, consider the circuit given, the output voltage V0 is. Now, there is negative feedback here. Op-amp tries to keep these two potentials same. Op-amp is basically an error amplifier. The error between the two terminals is quite small. So, we can consider this to be 0. So, if there is some current I here, there is the same current I. So, if you apply KVL, your I is going to be 2 by 1K plus 1K. It is going to be 1 milliampere. So, the current here is 1 milli. Now, op-amp draws no current as the input resistance of op-amp is very high. So, if this is I, this should also be I. If this is I, this should also be I. But we want to find V0. We want to find V0 here. So, let us finish the problem. Give me a KVL round this loop to finish this. So, it is I into 1K plus I into 1K plus V0 is 0. So, your V0 is minus I into 2K. I is 1 milli into 2K. So, V0 is going to be minus 2 volts. V0 is going to be how much? Minus 2. So, your V0 is going to be how much? Minus 2 volts. Go through the question. Assuming VB1 equal to VB2 equal to 0.7, VB3, there is 2 NPN transistors, each are given 0.7, and there is a PNP which also has a 0.7 forward drop. Find the DC current I0 if all the transistors have the same beta of 100. So, beta is 100 given. So, we are supposed to find I0, but before that let us apply Ohm's law. We have to find the base voltage here, VB, so that your I0 is beta times of IB. Your I0 is simply beta times of IB, but what is IB here? What is IB? You already have 10 volt and there is 0.7, 0.7, 0.7. The base voltage is going to be 10 minus 3 times of 0.7, 2.1. So, that is going to be 7.9 volts. Your base voltage is 7.9. So, IB is VB by 395, and what is your I naught? I naught is going to be beta times of IB. Beta is 100 and IB is 7.9 by 395K. So, try to calculate this. Try to calculate. I do not have a calculator. Try to calculate this. 100 into 7.9 by 395. 100 into 7.9 by 395. It is coming around 2 milliampere. 2 milli. 2 milli. Good. Aman, 2 milli. So, the diode forward drop is 0.7. So, we are stuck with 3 diodes here. Each diode gives a drop of 0.7. The base current is VB by 395. Your I naught is beta times of IB. Neglect the channel length modulation. The approximate output peak voltage V naught is in millivolts. Now, here you can see there is a differential amplifier. There is a differential amplifier. Now, what is the definition of op amp? Op amp is basically a high gain differential amplifier. It has 2 terminals, the non-inverting and inverting. At the non-inverting terminal, you are given 2 millivolts. 2 millivolts. At the inverting terminal, an output you have a 4K and 1K. So, this is simple non-inverting amplifier, okay. And this transistor you can treat it as a buffer at the last stage. So, the gain of a buffer is generally 1, okay. So, now this is a simple model of an operational amplifier. This is a standard circuit. Your V naught is going to be 1 plus 4K by 1K into 2 millivolts. So, it is 5 into 2, that is going to be 10 millivolt. This is a solution. Or you can do like this. Whenever there is negative feedback, the error between the 2 terminals will converge. The voltage at non-inverting is the voltage at inverting. And then op amp draws no current, the gate terminals draw no current. You can apply something called the voltage division rule. So, by voltage division, if there is a voltage division will always give you a fraction of the input voltage. So, across 1K, if you have 2 milli, across 4K you will have 8 milli. So, 8 plus 2 is going to be 10. So, you can do like that, or you can apply voltage division. 2 milli equal to V naught into 1K by 4K plus 1K. So, your V naught is 10 millivolts. That is the solution. So, go through the problem. Find the value of beta of the transistor if VB is given as minus 1 volt. If VB is given as minus 1 volt, for the circuit shown, consider VB as 0.7. This should be VB, it is not VEB because this is an NPN, VB as 0.7. So, when you go down, the voltage at emitter should be 0.7 less than the base. So, minus 1 minus 0.7 is going to be minus 1.7. So, now you are asked to find beta. What is beta? If I know the emitter current and if I know the base current, then 1 plus beta is equal to IE by IB. So, from this expression we can find beta. Okay. So, what is IE? IE is minus 1.7 minus of minus 3 by 4.8. This is your IE. And what is IB? IB 0 minus of minus 1, 0 minus of minus 1, 0 minus of minus 1, which is 1 volt, by 50K. So, this is going to be 1 plus beta. So, from here you can calculate beta. So, from here you can calculate the value of beta. So, the current here is potential difference by resistance. There is already minus 3 here, minus 1.7 minus of minus 3. Potential difference by resistance. According to Ohm's law, if you have two voltages V1 and V2, there is a current I is equal to V1 minus V2 by R. V1 minus V2 by R. Have you understood now Ohm's law? Is it okay? I have applied Ohm's law here. Okay, fine. So, what is the value of beta anyway? What is the value of beta? Aman says 12.54. So, let me 3 by 4.8, 1 by 50 minus 1, 12.54. Good. Aravind, Aman, very good, 12.54. So, go through this problem. Why minus 1.7? Why minus 1.7? See here, there is a diode here. Always remember, cathode is cathode voltage is always base voltage minus 0.7. Can you see that there is a 0.7 drop here? Can you see here? There is a 0.7 drop. So, this voltage is base voltage minus 0.7. Have you understood now? Already the base voltage is at minus 1 minus 0.7. That is why it is minus 1.7. Okay? Yeah. Now, if VBC is 6 volts, VBC is 6 volts, VEB, oh this is a PNP transistor, not NPN, VEB is 0.7, beta is 75. 75, the lights are blinding, I am not able to see. The value of RC, okay, you are asked to find RC. You are asked to find the collector resistor RC. Now, what is the total voltage from between collector and emitter? You already have 0.7 and this is 6. 0.7 plus 6 is 6.7. 0.7 plus 6 is 6.7. So, voltage is always measured with respect to ground. So, VE minus 0 is 0.7, VE minus 0 is 0.7, so VE is 0.7. Here you have IE, this is IC. So, let us find IE first. IE is going to be 12 minus 0.7 by 10K. And what is IC? IC is alpha times of IE, which is beta 75 by 76 into IE. So, you will substitute the value of IE here. And what is this voltage? This voltage is going to be VE minus 6.7. 0.7 minus 6.7, it is minus 6 volts. It is going to be minus 6. So, now you can tell the value of RC by Ohm's law. RC is going to be the same formula I told you before. Do not forget Ohm's law, okay? Do not forget Ohm's law. Ohm's law says the current is potential difference by resistance. So, if anybody has trouble with Ohm's law, please follow that. The current here is potential difference by resistance. So, the resistance is V1 minus V2 by I, which is IC. So, substitute the value of IC. Substitute the value of IC. So, 12 minus 0.7 is 11.3, 1.13 milli. So, this is almost 1.13. Please substitute 6 by 1.13. So, approximately 6 by 1.13. it is around 6 by around 5.18, 5.2K, around 5.2, okay, 5.2K we are getting. This is the value of RC, okay. So, I have done nothing here, voltage is always measured with respect to ground. So, this voltage is VE minus 0 is 0.7, so your VE is 0.7 and VBC is given 6. So, the voltage between the 2 points is 0.7 plus 6, that is 6.7, and this voltage is 0.7 minus of minus 6, or this voltage 0 minus VE is 6. So, this voltage is going to be minus 6 anyways. So, IC is there, RC by Ohm's law is going to be this value. So, try to calculate RC. Go through the question. In the given circuit, VCC is 5 volts, beta is 100, beta is 100. If RC is Rx, then VC is 2 volts. If RC is Rx, then VC is 2 volts. If RC is Ry, then VC is 1 volt. If RC is Ry, then VC is 10 volt. What is Rx by Ry? Now, the IC always depends on IB. Please do not forget, in a BJT, the current will never depend on the load. This current IC will depend only on IB. So, whatever the examiner is telling, the IC actually remains same, because IC only depends on IB. So, what is IC here? IC is 5 minus 2 by Rx. In the first case, it is 5 minus 2 by Rx. In the second case, it is 5 minus 1 by Ry. 5 minus 2, when it is 2, RC is Rx, when it is 1, it is Ry. So, the solution is ready, Rx by Ry or Ry by Rx. What do we want? Rx by Ry. Rx by Ry is going to be 5 minus 2 is 3 by 4, it is 0.75. Just see the calculation, your Rx by Ry is going to be 0.75, and please mind you, the collector current depends on the base current and the collector current is independent of the load resistance. So, whatever the scenario examiner is giving, the IC remains same, there is no change in the IC value, okay. Okay, so go through the problem. Find the value of RC for the BJT to be in the forward active mode if beta is 100 and VBE is 0.7. VBE is 0.7. This is IB, this is IC. And VC sat is 0.2. What do we want here? Find the value of RC for which the BJT is in for. See, the examiner wants you the value of RC for which it is still in active region. What do you mean by it is still in active region? It is at the edge of saturation, which means this VC can be taken as 0.2. So, he want this is the characteristics. So, at this VC 0.2, he wants the value of RC here. He wants the value of RC where it is still maintained in active region. Now, IC is still beta IB because you are at the edge of saturation. So, how do we find RC now? Tell me what is RC? RC is directly equal to 10 minus 0.2 by IC. This is the answer. So, 10 minus 0.2 is going to be 9.8 by IC is beta times of IB. IC is beta times of IB. What is IB? 5 minus 0.7 by 430K. 430K. Please substitute beta equal to, how much is beta? 100. Please substitute beta equal to 100. It is 9.8 by 100 times of 4.3 by 430K. So, this is the value of RC. This is the value of RC. Aman says 9.8K. Let me calculate. 9.8. So, RC should be less than or equal to 9.8K. What happens if RC is still less? Then the drop will be less, then the VC tries to increase, the BJT will try to move towards the active region. So, your RC should be lesser. Example, what if RC is 0? If RC is 0, it is still inactive, then you will have 10 volts somewhere, you will operate somewhere here. So, RC should be less than 9.8. Very good. Durga Prasad, Aman, very good. Now, estimate the range of the possible solution. I have converted it into a numerical problem. You are asked to find V0 DC. In the figure, all transistors are identical and have high value of beta. The value of the voltage VDC is equal to. So, here the data is VB on should be given as 0.7 as in most of the problems, because if there is a possible solution, then the examiner does not have to give, you can assume. But since this is a numerical session, I have to include in the question VB on is 0.7. So, when it is 0.7, this is a current mirror circuit. In a current mirror, this transistor and this current both should be same. Here you can see there is 0.7 here and 0.7. So, the total voltage is going to be 1.4. So, what is this current I? The current I is 5 minus 1.4 by 1K. It is around 3.6 milliamp. So, these two currents should be same. So, now you can find your V0 DC. V0 DC is simply equal to 5 minus I into 0.5K. That is the solution. So, 5 minus 3.6K into 0.5K. So, 5 minus 1.8. 5 minus 1.8 is 5 minus 1.8. So, that is going to be 3.2. It is going to be 3.2 volts. Okay. So, this is your V0 DC. Find ID if the given MOSFETs are similar and the threshold voltage is 1 volt. Mu Cox W by L is given as 2 milliampere per volt. You are asked to find the drain current ID. You are asked to find the drain current ID, is it not? Now, since MOSFETs are given similar and whenever gate and drain are shorted, they are in saturation. So, you can simply say X plus X is 4. X plus X is 4, that means X has to be 2. So, your VGS is 2 volt. Okay. So, let us calculate. In saturation, ID is mu Cox W by L, K times of VGS minus VT whole square by 2. So, substitute and finish the problem. It is 2 milli, VGS is 2 volt minus 1 whole square by 2. So, 2 minus 1 is going to be 1, 1 square is 1. So, it is almost 1 milliampere. just check, it is 1 milliampere. Considering the channel length modulation, the small signal drain to source resistance of all MOSFETs is 1 mega ohm. So, here in this problem, R naught is given as 1 mega ohm or RDS is given as 1 mega ohm, and mu Cox W by L is 1 milliampere per volt square. Then the small signal voltage gain is. Now, you can see this is a simple common source amplifier, a common source amplifier. Input is given at gate, output is taken at drain. So, for a common source amplifier, what is the standard formula for calculating the gain? The standard formula for calculating the gain is minus GM into output resistance. So, what is the output resistance? It is, here you have R02 and this is R01, because this is a drain terminal. At the drain terminal, you have R0. So, it is R01 parallel R02, which you can substitute. So, that ends the problem. Now, just find GM. What is GM when, what is given? Yeah, mu Cox W by L is already given. So, here 2 milliampere is there. This is a current mirror. So, if this is 2, this is also 2 milli. So, what is GM? GM is simply root 2k into ID. So, 1 milli into 2 milli. So, that is around 2 milliampere per volt. So, let me substitute 2 milli into 1 mega parallel with 1 mega, that is given. So, how much is 1 mega parallel with 1 mega? That is 1 mega by 2. So, 1 mega by 2 into 2. So, 2 gets cancelled. The gain is going to be, is it given 1 mega? Yes, minus 10 power 6. The gain is going to be how much? R01 parallel R02. It is 1 mega ohm. 1 mega ohm parallel 1 mega. It is minus 10 power 6 into 1 milli. So, it is minus 1000. It is going to be minus 1000 milli and mega. So, this is going to be 0.5 mega, 0.5 into 2. So, oh, it's, I am getting 500. So, this is 1 mega parallel 1 mega minus 2 milli into 0.5 mega into 0.5 mega. So, it is going to be minus 1000. Minus 1000 is the right answer, right. So, just check 1 mega parallel 1 mega, it is going to be 0.5 mega, 0.5 into 2. So, students have got 500. Aman, CR7, please check. I was observing your answer and I was thinking, how come it's, what is the mistake we have done? I think 1000 is correct. Please check. I think 1000 is correct, because 1 mega parallel 1 mega is going to be 0.5 mega. So, 0.5 mega into 2, it is going to be 1000. Please check. Yeah, it is 1000, right? Yeah. The given MOSFET operates at the edge of saturation. Find the W by L if mu n Cox is 300 micro and VTH is 1 volt. So, what is that we want? We want W by L. So, again it is a substitution problem. Given ID is K times of VGS minus VT whole square by 2. So, mu Cox is 300 micro, it is 0.3 milli into W by L, VGS is 2, VT is, how much is VT? 1 whole square by 2. This is your ID, this is your ID. And what is ID here? The MOSFET is at the edge of saturation. At the edge of saturation, your VDS is equal to VGS minus VT. So, it is 2 minus 1, it is 1 volt. VGS is given as 2 volt So, it is 1 volt. So, please substitute ID equal to 5 minus 1 by 2K. From here you can get W by L. So, 5 minus 1 is 4, 4 by 2 is 2 milli. So, 2 2s are 4, it is 4 divided by 40 by 3, it is getting 40 by 3, it is around 13.33. Just check, I am getting 30.33, 13.33. This is the solution. Now, for the given MOSFET, the threshold voltage VTH is 3 volt, mu Cox W by L is 1, the drain current ID is, you are asked to find the drain current ID, the threshold voltage is given as 3 volt, 3 volt. Okay, so let us start the problem. By voltage division, the gate voltage, first let us calculate, VG is going to be 20 into 1K by 9K plus 1K. It is going to be 2 volt. So, the voltage here is 2. Now, please just wait a minute. VTH is given as 3, but the gate voltage is only 2, meaning this MOSFET is in off state. When the MOSFET is in off state, the drain current ID will be 0. The drain current ID is going to be 0. There is no question of calculation, because for a BJT to be on, at least 0.7 you have to have, but for a MOSFET to be on, at least VT is needed. But the gate voltage happens to be only 2 volt. The threshold voltage is given as 3. So, that is the reason the drain current is 0, the MOSFET is in off state. So, your ID is going to be 0. Okay. Now, consider beta of the transistors to be infinite. The value of current I naught is, so the value of current I naught is, so how do we find I naught? Now, by voltage division, you have 5 volt here. Whenever there is negative feedback, the voltage at non-inverting converges at the voltage at inverting. So, this is 5. So, 5 by 2K is I naught, 5 by 2K. It is 2.5 milli, and mind you, whenever the beta is large, the emitter current and the collector current both are same, and op amp draws no current. Op amp never draws any current, and this is a negative feedback problem. You can simply apply something called virtual short. You can simply apply something called virtual short. Okay. The diode forward drop is 0.7, and op amps are ideal. The output voltage V0 is, how do you solve this problem? See, a similar problem we would have done in the class where diodes are tied at a common point. When diodes are tied at a common point, the diode that experiences more potential difference will switch on. For example, 1, 3 and 4. So, this 4 minus 0.7, you will have 3.3 here, and these two diodes will go to off state. This is something we have done in the class. Okay. Now, similarly, with no violation of Kirchhoff's law, we have 1 volt, 3 volt, 4 volt. So, in this 3, 4 is larger. So, your VOP is more positive than the other two. The diode is on, there is negative feedback. So, this is a very simple problem. You have 4 volt and there is negative feedback, 1K and 2K. The diode is here. So, now you tell me what is V0? The standard problem, V0 is a non-inverting, this is a non-inverting amplifier. So, your output is going to be 1 plus R2 by R1. Your output is going to be 1 plus R2 by R1 into 4. So, it is going to be 12 volt. So, this is the solution, and once it is 12, here the D2 and D1 diodes are going to be in off state. The D2 and D1 diodes are going to be in what state? Off state. So, virtual short here is only due to this 4. If this is 4, this node is at 4, you can apply KCL, entering current is leaving. So, this is your V naught. 0 minus 4 by 1K is 4 minus V naught by 2K. 0 minus 4 by 1K is 4 minus V naught by 2K. So, your V naught, if you solve, you will get 12 volts. Okay. So, go through the problem. The slew rate of an op amp is 1 volt per microsecond. Slew rate is given as omega Vm. It is 1 volt per microsecond. Okay. So, let us see what we have to find. The maximum value of frequency to avoid slew rate induced distortion. So, he is asking you omega, and what is V naught? V naught is 1 plus R2. Oh no, this is an inverting amplifier. Mind you, input is given to inverting, unlike the previous problem. So, your V naught is minus 10K by 1K into 10 sin omega t. So, now 10K by 1K, it is going to be minus 100 sin omega t. So, 100 is the peak value. So, let me substitute here 100. So, now what is omega? Omega is going to be 10 power 6 by 100. It is 10K radians per second. It is going to be 10K radians per second. How can we say that the op amp is in negative feedback? Yeah, see, whenever the output is fed back to minus terminal, it is obviously negative feedback. But when both feedbacks are given, then you can open circuit the op amp and you can connect some test voltage here and backtrack. Whenever the voltage at inverting is more than non-inverting, it is negative feedback. If the voltage at non-inverting is more than inverting, it is positive feedback. So, you can do that test, but here there is no need to check, because directly the output is fed back to the minus terminal. So, it is supposed to be negative feedback. Okay. Okay, so try to do this. Consider the amplifier circuit shown below. Assume op amp ideal, then the voltage gain V naught is V naught by V in is. Now the upper one is a non-inverting amplifier, but the lower one is inverting. The lower one will give you minus R2 by R1 times of V in, minus 2K by 1K times of V in. It is going to be minus 2 V in. It is an inverting amplifier. Now the upper one is non-inverting, so it is 1 plus R2 by R1 times of V in. It is going to be 4 V in. So what is V naught? V naught is simply the difference between the two, 4 V in minus of minus 2 V in. So your V naught by V in is 4 plus 2 is 6. So your V naught by V in 4 plus 2 is going to be 6. So these are standard formulas. So one is the inverting amplifier, the other one is the non-inverting amplifier. An ideal op amp circuit is shown below, then the value of load current is. So how can you calculate the value of load current? And op amp tries to keep these two voltages same. So imagine I have two resistors. Suppose this node is Vx, then this node is also Vx. So you have 1K and 100. Here you have IN. Now whenever two resistors experience same potential difference, like for example in a parallel connection, you can apply something called the current division rule. So, similarly here these two potentials are same, this potential is same, and since op amp draws no current, you have 1 milliampere flowing here. So, in this problem also you can apply current division and finish it. So, what is current division? The branch current is equal to the total current into opposite arm by sum. So, your IL is going to be 1.1 K, 1.1 by 100. So, 1 K plus 100, it is 1.1 K, 1.1 by 100. So, how much is IL? How much is the total current IL? 1.1 around 11 milliamp, 1.1 by 100, that means if I put 0, so I think it is 11 milliamp, 1.1 by 100, yeah, 11 milliamp. So, this is by the current division formula. Otherwise, you can take an extra node here, but that takes time. You have to solve an extra equation for that. Okay, you can take an extra node Vy and calculate. The given op amp is ideal and the forward drop is 0.7, then the output voltage V0 is now when a negative voltage is given to negative terminal, please watch carefully. When a negative voltage is given to negative terminal, the output is positive. When the output is positive, the diodes are on. When the diode is on, there is negative feedback. So, what is this voltage? It is V0 minus 0.7. The cathode is always less than the anode by 0.7. Now, you can apply KCL and finish this problem. I1, I2 and I3, this is virtually 0. So, now you can find V0 by KCL. I1 plus I2 is equal to I3. What is I1? I1 is V0 minus 0.7 minus 0 by 6K, V0 minus 0.7 minus 0 by 3K is 0 minus of minus 1 by 1K, which is 1 milliampere. From here you can find V0. So, what is 1 by 6 plus, that is 2, 2 plus 0.7, I think 2.7. This is something like 6K and 3K are in parallel. So, hopefully you should get 2, 2 plus 2.7, 1 by 6K plus 3K. So, that is going to be 2K plus 0.7, 2.7 volts is the right answer. Why did this come again? The forward drop is okay. So, just to differentiate between the previous problem, you can see when a positive voltage is given to negative terminal, the output is negative. When the output is negative, these diodes are in off state. When the diodes are off, this op amp goes into open loop. In open loop, the output is either plus Vsat or minus Vsat. It is either plus Vsat or minus Vsat. So, since the voltage is given to minus, your V0, it will hit the negative rail voltage, which is minus 15. So, that is the solution, because here the diodes are in what state? Off state. So, your V0 is going to be minus 15 volt. Okay. Oh, this is multiple select. See, it is my personal suggestion to you. Whenever multiple select questions is given in theory, please do attempt it. But when they are given problems like this, it's like doing two problems. So, you can actually wait until all the other questions are done and then you can come back. But if there is a theory given, and definitely you can easily attempt it. But now you can see in this problem, he has given both the clauses for Vin greater than this voltage and Vin less than this voltage. So, it's like doing two problems. Okay. So, before that, let us apply voltage division. What is this voltage? Minus 15 into 1K by 2K plus 1K. So, it is understood because in the options minus 5 is written. So, this node is at minus 5 volt. So, now there is a comparison between non-inverting voltage and inverting voltage. The non-inverting is at minus 5 and the inverting voltage is Vin. Okay. So, what happens when the inverting voltage is greater than non-inverting? When Vin is greater than minus 5, the output is negative. When the output is negative, the diode is on. So, when the diode is on, this diode is off, then this node voltage will be manifested here because the diode is off when this is negative. What is this voltage? This voltage, you can see, if this is minus 5, this will be minus 5 because of virtual short. So, this node is going to get manifested when this is off. So, when Vin is greater than minus 5, your V naught is minus 5, but Vin is greater than, when Vin is greater than minus 5, your V naught is minus 5. Here options are not seen here. So, some printing problem is there. When Vin is greater than minus 5, your V naught is minus 5. If it is there, then option B is the right answer. And then please check for Vin less than minus 5. So, it is like doing 2 times. Whenever Vin is less than minus 5, the non-inverting is greater than inverting, your VOP becomes positive, this diode is on. There is again negative feedback. So, you can apply something called virtual short. So, Vin minus of minus 5 by 1K is going to be minus 5 minus V naught by 1K. So, your V naught is minus Vin plus 10 minus 5, this is plus, it goes 10. So, this hopefully this C bit. So, you can see now 2 options are correct here, option B and option C. Option B and option C are correct. So, that is my personal suggestion. Whenever it is messy with too much numericals and it has multiple select, first do some simple problems and then you can come back. But if it is theory, you should definitely try. Okay. The capacitor is initially charged to 8 volt. The capacitor voltage at T equal to infinity. So, this is a very simple problem. Once you close the switch, the capacitor is not charging, it is discharging. But here you can see this is permanently 3. So, slowly the capacitor will discharge from 8 to 7, 7 to 6, 6 to 5 like that till it touches 0 volts. So, capacitor is not charging, it is discharging. So, it will drain to 0. Find the capacitor voltage Vc in its steady state at T equal to infinity if the switch is closed at T equal to 0. Capacitor is initially uncharged. What is it? Vt is minus 2 is the threshold voltage. So, now in this problem, the capacitor here permanently again you have given 4 volt. So, this capacitor will keep on charging, say from 0, 1, 2, 3 like that till it touches 8 volt, because permanently in the previous problem or this problem permanently you have given VGS equal to 3 or 4. So, definitely it will go to its steady state till this transistor, this MOSFET goes to triode region. Even in triode current will flow, do not forget it is not just in saturation, even in triode the current will flow until it touches 8 volt. So, these are simple questions. For the PMOS circuit, the threshold voltage is minus 2 volt and mu Cox W by L is 1 milliampere. Calculate V naught DC. So, now you can see your ID is K times of VSG minus mod VT whole square by 2. So, this is the PMOS equation. Okay. But the VSG is nothing but the voltage across 200K. The voltage across 200K is your VSG. So, how much is it? It is 15 into 200 by 300 plus 200. So, 300 plus 200 is going to be 5, 5 3s are 15, it is 6 volts. So, there is 6 volts here. So, you can substitute here 1 milli, it is 6 Vt is 2 volt whole square by 2. So, just do the calculation. 6 minus 2, 6 minus 2 is 4, 4 square 16, 16 by 2, 8 milli. Please tell the topics which require more focus. Very good, that is a good doubt. So, these are simple network problems. So, only last problem is there. This one is the common gate amplifier. Okay, I thought common source, it is common gate. So, you are asked to find V0 by V. So, let me write a common gate here. So, here you have RS and this is RD. Please substitute the values. So, I am just expecting that since RS and RD are there, you can just do it. Okay. So, you are asked to find V0 by V. So, what is V0? If this is ID, it is minus IDRD by what is Vin? It is minus VGS plus IDRD. Divide numerator and denominator by ID. So, you will get the voltage gain as minus RD by VGS by ID is 1 by GM plus RS. So, please substitute this, you will get the solution of the common gate amplifier. Like somebody was asking me, what are the topics? Please see here, op amp analog comes with 3 topics usually, analog circuits. So, we have diodes, BJT and MOSFET and op amp, that is all. So, these are the 3 topics. Now, which one a student has to focus? Diodes with resistors, one question will come on diodes with resistors and diodes with capacitors, okay, one question. In BJT for electrical students, DC analysis pakka you are going to get, DC analysis every year one question will be there. For EC students it is an option, but for electrical students and instrumentation, DC analysis in BJT is pakka. DC analysis in MOSFET is 100% for EC students, EC. But for triple E and instrumentation, DC analysis in BJT pakka you are going to get. AC analysis 100% one question, AC analysis of MOSFET. For triple E, for EC students and triple E students, AC analysis in MOSFET, one question you will get. Op amp, please focus more questions on negative feedback. Positive feedback is just a switcher where the output is either plus VSAT or minus VSAT, but negative feedback is, these negative feedback questions you will find even in network textbooks also. You have to just apply virtual short and solve, okay. So, if you can classify problems like this, it becomes simple. If you take every topic, it becomes cumbersome, okay. Diodes with resistors, diodes with capacitors, you have to solve. BJT and MOSFET, DC and AC analysis. In that DC analysis of MOSFET, very important for EC, DC analysis of BJT, very important for triple E. For op amp, please focus on negative feedback questions. Okay, so I think 1 hour is over. My best wishes to you. Keep in touch. This is my phone number. So, if you have any doubts, you can post. Okay. Thank you all. Thank you for your patience. Good luck.